So here we go. So what is a fractional age assumption? So if you look at a life table, you've got the L-axis, right? You've got the Q-axis, but you've got them only at integer ages. So whenever you want to do something that goes beyond an integer age, you'll need to make additional assumptions. You'll need to figure out how to do that, right? And that's also one of the big differences between what we did in chapter 2 and what we're doing now in chapter 3. So in chapter 2, everything was purely mathematical. And there we were reasoning with our survival functions, for instance, in continuous time. Whereas in chapter 3, we say, okay, instead of using these purely mathematical concepts, we'll need to get our data from somewhere. And we're going to download a life table, a mortality table. And then using that table, we need to do our calculations somehow. So we need to make certain assumptions in order to be able to do these calculations. And that's exactly what we mean with a fractional age assumption. It's an assumption about the probability distribution for the future lifetime random variable in between two integer ages. And we're going to discuss two widely used assumptions, and you're allowed to use them as long as you refer to the particular assumption that you're using, and you're allowed to use these, for instance, during this week's computer lab. The first one is called the uniform distribution of deaths with acronym UDD. And then the second one is called the piecewise constant force of mortality. So I think you can already figure out what the second one would mean. So you've got the force of mortality, you've got mu x, and in between two integer ages, you're going to assume that the force of mortality stays constant. So you've got a piecewise constant force of mortality. So I'm going to take a little bit of time to work with these assumptions, because I think, once again, that builds up good foundations for you to be able to work with these things in exercises and in practical problems. So let's formulate the UDD, so the uniform distribution of deaths. We've got two equivalent ways. For the first one, we could say, well, if you take an integer x, and if you look at a duration s, where s takes a value between 0 and 1, then the sqx is equal to s multiplied with qx, right? So on the left-hand side, I'm referring to what's the probability that an x-year-old will die before reaching age x plus s. So here the s is really a subscript. And here on the right-hand side, I'm making my UDD assumption, and then it turns out that I can quickly obtain this mortality probability by multiplying the qx, the 1-year probability of dying, with the duration s that I consider. And this only holds for an s between 0 and 1, of course. An alternative way of putting it is perhaps a little bit more difficult, but really makes the connection with the uniform distribution and the uniform term that I have in this in the name of this assumption, right? So here I assume that I can write the tx, the future lifetime of the x-year-old in continuous time. I can write that down as kx, that's the integer part of my tx, right? That was the floor function applied to tx, plus a remainder rx, and this remainder rx takes a value between 0 and 1, right? And under the UDD assumption, it turns out that this rx will follow a uniform distribution between 0 and 1, and that the rx is independent of the kx. Yeah? So these are equivalent ways to formulate this assumption. And of course, what mathematicians then do is they play with this assumption. So we're gonna show that if you assume number 1, that then number 2 is also following. And if you assume number 2, then that you can easily obtain number 1, right? So we're gonna play with the equivalence of these two ways of putting the assumption. So maybe let's look at the bottom. Do you see what I mean over there? So the kx, that's the integer part of the tx. So that's my floor function applied to tx. So that means if I have the kx, the whole number of years that my individual survives, that if I add something to it, this Rx, then that this Rx should be a number between 0 and 1, right? It cannot exceed 1, because otherwise I would have to make the Kx a little bit larger, right? And it can also not be negative. So let's say that Tx is 16.3, then the Kx is 16, and then the Rx is 0.3, right? That's how you should see it here. So what we're gonna do now is we're gonna start, and you see that here in my title, we're gonna start from the number 1 assumption, and we're gonna show that number 2 then also holds. So remember number 1, that was the assumption that SQX is equal to S multiplied with QX, right? And number 2, that was about the Rx being uniformly distributed between 0 and 1, and the fact that Rx and Kx are independent. That's what I need to show. So if I need to say something about the distribution of this random variable Rx, then I can start with looking at the CDF of this Rx, right? So I'm going to look at the probability that Rx is less than or equal to S. And that I can write using the following expression. So I can say that's the sum over all K of the following probability. So what kind of law am I applying here? Okay, so if I sum over all the values K, and I take this joint probability, then I'm looking at this probability that I'm interested in. Now, one way to rewrite this expression is, if Kx is equal to K and Rx is less than or equal to S, then I'm in fact looking at the probability that Tx is in between K and K plus S. That's exactly the same, right? Because I know that the integer part is equal to K, the remainder is less than or equal to S, so that means that my future lifetime in continuous time should be between K and K plus S. But this probability, that's what we learned last week, and this probability I can calculate it. I can say, due to the multiplication rule, that is the probability of surviving until age x plus k for an x-year-old, so that is the kpx, multiplied with the probability of dying for an x plus k-year-old in a duration window of s years, right? So that's my sqx plus k. But now I know, of course, that the formulation of the uniform distribution of deaths, number 1 must hold. So that means that I can do something with this blue guy over here. I can write it as S, a number between 0 and 1, multiplied with qx plus k. That's exactly what my first version of the UDD is learning me. So if I put the S in front of the summation, I'm left with looking at this guy. And what you see here, that is exactly the probability function of the current future lifetime of the kx. So what you see over here, the kpx multiplied with the qx plus k, that is exactly the probability that kx is equal to k. We sum that over all possible values that k can take. So because we have here a well-specified probability function for k, kx, that sum should equal to 1, and we're just left with s, right? So what do we see? That indeed Rx, the CDF of Rx, corresponds to the CDF of a uniform distribution between 0 and 1. So we prove the fact that Rx is uniformly distributed between 0 and 1. The last thing we want to show now is that Rx is independent of Kx. So that's going to be the next step, and then I'll answer your questions and take a break, right? So let's do the next step. If I look at the independence between Rx and Kx, then I'm going to start from their joint probability. The probability that Rx is less than or equal to S and Kx is equal to K, right? That, and we did that on the previous sheet already, can be rewritten as the probability that Tx, the future lifetime but in continuous time, is in between K and K plus S. So if I work with my multiplication rule, this probability, like we discussed last week, is the probability of surviving until age x plus k for an x-year-old, multiplied with this mortality probability, the SQX plus k. So we're going to manipulate this guy because we know under the UDD assumption number 1, that we can multiply the S with the QX plus K. So what are we left with? We're left with the probability that Rx is less than or equal to S. That's just S because that's what we proved, that's what we've shown on the previous slide. And we multiply with the probability that Kx is equal to K because that's the probability function of my current future lifetime. That's something we learned last week. So what do you see? That the joint probability is equal to multiplying the marginal probabilities. And that's, that shows us then that the Rx and the Kx random variables are independent from each other. So what did we do? We started from the formulation number 1 of the UDD, and we showed the equivalence, or we showed that you can then obtain the UDD assumption as formulated in this second version, where you say that the Rx is uniformly distributed between 0 and 1 and independent of the Kx. Good. So what I was about to do is we showed that if you work with the uniform distribution of deaths, in one particular way that you retrieve the second way of putting the uniform distribution of deaths. And what we're now going to do is we're going to do that the other way around, right? So that means that what we want to show right now is that SQX will be equal to S multiplied with QX. And what we're allowed to use right now is that this KX and RX are independent, and that the Rx follows a uniform distribution of deaths, right? So we're going to start with the UDD as formulated in the second way, and we're going to look at this mortality probability. So SQX, that's the probability that Tx is less than or equal to S. We're going to work with an S between 0 and 1. That's because that's how we work with fractional age assumptions. How you want to say something about what's happening in between two integer ages. If Tx is less than or equal to S, well, then we can say that the Kx should be 0, right? Because if the Tx is below a number S that is smaller than 1, right? Then the Kx, the integer part of the future lifetime, should be equal to 0. Then the Rx should be less than or equal to S. Now, of course, we know that Kx and Rx are independent, so their joint probability reduces to the product of their marginal probabilities, right? And we also know that we can write this probability in blue because of the uniform distribution of the Rx. We can write it as just S, and the probability in magenta, that is exactly the 1-year probability of dying for an X-year-old. So that's just the QX. So we see, if we're willing to assume the UDD formulated in its second way with the Rx, the Kx, then we immediately retrieve the UDD as formulated in the first way, namely that the mortality probability, the SQX, can be written as the product of S and QX, right? So that was just to feel a little bit comfortable with these different concepts. And it's also a nice exercise. The transitions that we made over here are a nice way to check whether you really understand how to work with this Tx, with the Kx, and with the Rx. So just make sure that you understand these different steps. You should not be able to reproduce them, but you should be able to understand these different steps such that if I give you a small exercise that works with similar concepts, that you're able to solve that. If you work with the UDD assumption, then this will also bring you a way, or give you a way to work with, to build up reasonings like the one that I have here on the sheet. So what we're going to do here is we're going to look, or we're going to try to gain a little bit more insight in why this assumption is called the uniform distribution of deaths. We already encountered this uniform distribution in the distribution for the Rx random variable, but now we can think, yeah, why is it called the uniform distribution of deaths? So let's look at that. So if we start with SQX, our probability of dying, in fraction s of the year following hx, right? Then that is the complement of SPX. And this SPX, we can write it as Lx plus S divided by Lx, right? The Lx plus S will not be immediately available in our life table, but the Lx will be, because we have the number of survivors for each integer hx in our life table. So if I manipulate this expression, what I then know is that this SQX is equal to S multiplied with QX because of the UDD assumption. But S multiplied with QX can be written as S multiplied with DX divided by LX, because that's another way of expressing the QX. So what do I know then? That this guy over here, right, should be equal to the guy here at the bottom, right? And if I manipulate this expression, then that means that dx, s multiplied with dx must be equal to lx minus lx plus s. So that means the number of people who die between hx and hx plus s, I can write it as s multiplied with dx, where dx is the number of people who die between hx and x plus 1. So that's where the name is coming from. You here have the uniform distribution of deaths. So you know that in total at hx, the expected number of deaths is dx, and you're going to spread that uniformly between hx and hx plus 1. That's what this assumption then reduces to. Any questions on the transitions over here? And that is the one where we make the assumption of a piecewise constant force of mortality. So I must admit that the piecewise constant force of mortality assumption, that's the one that I often use most often use in my own research, because if you work with the econometric model building, then you're typically going to do that at the level of the force of mortality. So then it comes in handy to have an assumption there about this piecewise constant force of mortality. Yeah? So in many of the publications related to building mortality models, projecting mortality, building scenarios for future mortality, this assumption of piecewise constant force of mortality will be made. So how do I put this assumption? I'm going to assume that for an integer x and an s between 0 and 1, the force of mortality remains constant, right? It remains constant between hx and x plus 1. And let's say that the constant value there is equal to mu x star. Now, what is the nice idea, the nice thing about having a constant force of mortality? That it's a piece of cake then to do an integral calculation with this force of mortality, right? So that will come in handy. Because we discussed last week, that if you look at the survival function, you can express this survival function as the exponential of minus an integrated hazard rate. That's a very general expression in statistics. That's also how we can link here the 1-year survival probability, the px, to our force of mortality. But now you see immediately that if I do not have a specific function for this mu x, evaluated in S, then I would struggle to figure out how to evaluate this integral, right? But if I'm, of course, willing to assume that the force of mortality is piecewise constant, then I can just plug in here the mu x star, that is a constant when I calculate the integral over S. So then I quickly retrieve the following expression. So that shows us that if you're willing to make this assumption of piecewise constant force of mortality, that then calculating these integrals becomes very simple, and you can go from your force of mortality to any survival or death probability that you wish to calculate. Okay. So the other way around then, of course, is that the mu x star would then be equal to minus the logarithm of px. So again, Sally, I'm referring here to the natural logarithm. So I could also write that minus the ln of px. Does that make sense for everybody? You also see that it is a very elegant expression, right? And perhaps also that if you look at a life table, and you're able to get the px or the qx from the life table, that you then here have a quick relation to go from this px or this qx to the mu x, right? So it's just a way of denoting it here, but you can also drop the star. The main message here is that you have a constant value for your force of mortality between hx and x plus 1. All right, let's use a bit of similar calculations here. So what if we take an s between 0 and 1? And if we want to know what is spx, then that is the exponential of minus the integral from 0 to s of the mu x. And we take the integral over an integration variable, say u here, right? So if I do the manipulations, then I've got e to the power minus mu x multiplied with s. So once again, what makes it very easy to work here is that I can solve the integrals very quickly, that the integrals become very simple in this type of expressions. This, of course, can be written as px to the power s. So that is, in fact, what our piecewise constant force of mortality implies, that I can write a survival probability as px, as the 1-year survival probability px to the power s. So if I would further work with that, if I would say, what if I look at spx plus t instead of spx, as long as the t plus s stays below 1, so as long as I stay within this interval between hx and hx plus 1, then of course I get the same value mu x star over here, and I've got exactly the same expression. So the meaning here is it doesn't matter where you start with your interval of length s, as long as you let the interval start between hx and x plus 1, and as long as the interval ends below hx plus 1, then you get the same expression for your survival probability. So it's only about the length of this considered interval, as long as you stay within the boundaries of this interval between hx and x plus 1. Good. Some final considerations here. We discussed two types of fractional age assumptions. We've got the UDD on the one hand, and we've got the piecewise constant force of mortality on the other hand. So what we want to reflect a bit upon is, are these assumptions in fact a little bit similar when it comes to the approximations that they make? And that turns out to be the case. Why is that? Well, if I look at the QX, then under the assumption of the piecewise constant force of mortality, I can see that as 1 minus px, and px was, under the assumption of piecewise constant force of mortality, e to the power minus mu x star. Now I can say that approximately this expression must be equal to mu x star. And what would I then be using? What kind of mathematical concept am I then using? How do we call that? So we have the expression that Qx is approximately equal to mu x, the constant force of mortality. And if we work similarly for a duration t, if we work with tqx, then we've got under the piecewise constant force of mortality that this is 1 minus e to the power minus mu x multiplied with t. Again, if I build my Taylor series approximation, I've got t multiplied with the mu x, right? So the point that we want to make here is that also under the piecewise constant force of mortality, you would have a qx, which is approximately equal to the mu x, and then the tqx is t times this approximation, right? And that's something you also had with the UDD assumption, because there you would say that tqx is t multiplied with qx. So here you got quite a similar kind of reasoning. So what we see is that the approximation to the tqx is t times our approximation to the qx, and that's in line with what our UDD assumption does.